The next programming exercise I would like for you to do involves the solution of simultaneous equations by the use of Gaussian elimination. The description of the programming exercise explains Gaussian elimination in general terms, so it will be more helpful to start with a numerical example. Okay, this will be a numerical example of the solution of simultaneous equations. Simultaneous equations by Gaussian elimination. Gaussian elimination. We'll start with an example set of equations. Let's take x0 plus 2x1 plus x2 equal to 0. That's the first equation. Then 2x0 plus 2x1 plus 3x2 equal to 3 is the second equation. Then minus x0 minus 3x1 plus 0 times x2 is equal to 2 is the third equation. So we have a set of equations, three unknowns, x0, x1, x2, and three equations. If you study linear algebra, you take the course in linear algebra, they will first go through an exercise to determine if this set of equations has a solution, and if that solution is unique. We will assume that the set of equations has a solution. This example happens to have a solution, and that it is unique. Now, with any set of equations like this, and by the way, this is the kind of equations one would derive by analyzing a linear electrical network. With any set of simultaneous equations, there are two things that we can do to these equations, and the solution to the equations will stay the same. The first thing we can do is multiply any one of the equations by a constant. Multiply any equation by a constant. So if we multiply both sides of any of these equations by a constant, we haven't changed the set of equations. And the second thing we can do is we can add equivalent things to each side of the equation, and that won't change the set of equations either. So we can add any of the equations to another equation. Okay, and that will not change the set of equations. And we want to use this in developing a method to solve these equations. What I want to do now is write this set of equations in matrix form, because we will use matrices in our programming to solve this set of equations. So I can write a square 3 by 3 matrix, and I'll go column by column with 1, 2, minus 1 in the first column, 2, 2, minus 3 in the second column, then 1, 3, 0, 1, 3, 0 in the third column. This forms a square matrix. This square matrix can now multiply a column matrix made up of the unknowns x0, x1, x2, and we can set that equal to a column matrix of these known values on the right hand side of the equations 0, 3, and 2. And if you understand how to multiply matrices, you will see that this is exactly the same set of equations simply written in matrix form. We have 1 times x0 plus 2 times x1 plus 1 times x2 equal to 0. Well, that's exactly the first equation. 2 times x0 plus 2 times x1 plus 3 times x2 is equal to 3. That's exactly the second equation. Minus x0 minus 3x1 is equal to 2 is exactly the third equation. So we haven't, all we've done is written this set of equations in this matrix form, and symbolically we could write this as a matrix A, a square matrix A, times a column matrix X is equal to a column matrix B. The values in the square, this is the square system matrix, these are known values. In the A matrix, also we have known values in this B matrix. What we are solving for are the unknown values in the X matrix, the X vector. What we want to do in solving this set of equations is to manipulate this square matrix into what is called the upper triangular form. In this form of the square matrix, all of the elements below and to the left of the main diagonal will be 0, and we'll have values in the upper triangle of this, or the upper above the diagonal of this square matrix. Now, to accomplish this, we need to change the values below the main diagonal to 0. To accomplish this, we will multiply a row both sides, these three elements in the square matrix, also this element in this vector over here on the right. We will multiply that by a constant and subtract from the row in question. So I want to start by manipulating the values to get a 0 in row. This is row 1, column 0. So I first need to define a multiplier for row 1. Remember, we're starting counting row 0 and then row 1, and this multiplier m, this will be equal to, since I have to multiply the first row by a constant and then subtract that entire row from the second row, that constant will be given by the value of in row 1, column 0. This will be A in row 1, column 0, divided by the value of the matrix A in row 0, column 0. So that's going to be 2 divided by 1. Our multiplier is equal to 2. We're going to take this multiplier, multiply by the first row of this system, and then subtract that result from the second row. So for the second row, we've got a 2, a 2, a 3, and then I have to include this 3 here. Now I want to multiply the first row by this constant. 2 times 1 is 2, 2 times 2 is 4, 2 times 1 is 2, 2 times 0 is 0. So then I'm subtracting all of that. So this is row 1. This is row 0 times our multiplier, And when we complete the subtraction, we get 2 minus 2 is 0. 2 minus 4 is minus 2. 3 minus 2 is 1. 3 minus 0 and is 3. This becomes the new row 1. So I can now, let me rewrite this set of equations. In the A matrix, row 0 has 1, 2, 1, and 0. The new row 1 has 0, minus 2, 1, and 3. And then the old row 0, 1, 2 is minus 1, minus 3, 0, and 2. Minus 1, minus 3, 0, and 2. And if I fill in the rest of these items, this now is the rewritten set of equations. It has exactly the same solution as the original set. So by multiplying the first row by a constant and subtracting that result from the second row, we've managed to get a 0 in below the diagonal, and we haven't changed the solution of the equations. I'm sure some of you caught my mistake. I said the right thing in coming up with this multiplier, but I wrote down a 2. That needs to be a 1. So the multiplier for row 1, A10 divided by A00 is 2 divided by 1. 2 divided by 1, and that gives a 2. So now the next step is to work on this entry in row 0, 1, 2, row 2, column 0. We make that into a 0, and we do that again by multiplying row 1 by a constant and subtracting that result from row 2. Now the multiplier, so I need to develop a new multiplier. So let's see, this is the multiplier for row 0, 1, 2, m, and just like we did in finding the multiplier for row 1, I'm going to take the value A20 in this case, A20, and divided by A00, and that's going to be minus 1 divided by 1. Minus 1 divided by 1. So the multiplier is equal to negative 1. So now I'm going, this is for row 2, so row 2, row 0, 1, 2 is minus 1, minus 3, 0, 2. Minus 1, minus 3, 0, 2, and then I'm going to subtract row 1 after multiplying by a negative 1, so that's going to be negative 1, negative 2, negative 1, 0, negative 1, negative 2, negative 1, 0. So this is row 2. This is row 0 times the multiplier, and I'm subtracting now. Minus 1 minus a negative 1, so that'd be 1 plus 1. I'm sorry, minus 1 plus 1 is 0. Minus 3 plus 2 is minus 1. 0 plus 1 is 1. and 2 minus 0 is 2. This is the new row 2. So I can rewrite the set of equations, and let's see. We had in the first row 1, 2, 1. In the second row 0, minus 2, 1. In the third row, the new this is row 0, row 1. The new row 2 is 0, minus 1, 1. That multiplies x0, x1, x2, and that's equal to 0, 3, and now we have 2 again, and this is the rewritten set of equations that again has exactly the same solution as this first set of equations. However, we've got 0 in the first column below the main diagonal. Let's do this one more time, but this time I'm going to work on row 2 to get a 0 in column 1. Now, so I'm going to have a multiplier. I want to multiply now row 1 and subtract that result from row 2. I need a new multiplier for, I'm working on row 2 again. This multiplier is going to be A, capital A, row 0, 1, 2, row 2, column 1, A, 2, 1, divided by A, row 1, column 1. So this is divided by A, 1, 1. So that's going to be minus 1 divided by minus 2 is equal to 0.5. So I want to multiply row 1 times 0.5 and subtract that result from row 2. So let's see, I'll write in row 2, which is 0, minus 1, 1, 2, and I want to subtract, this is row 2, I want to subtract row 1 times the multiplier, so 0.5 times 0 is 0, 0.5 times minus 2 is going to give minus 1, 0.5 times 1 gives 0.5, and then 3 times 0.5 gives 1.5, and now we subtract. 0 minus 0 is 0, minus 1 plus 1 is 0, 1 minus 0.5 is 0.5, and 2 minus 1.5 is 0.5. This is the new row 2, and I can rewrite the set of equations. First row 1, 2, 1, and a 0. Second row 0, minus 2, 1, and a 3, and then the new, so as row 0, row 1, the new row 2 is 0, 0, 0.5, and 0.5. Fill in the rest of these items, x0, x1, x2 equal to 0, 3, and 0.5. Okay, so this completes the first step. We have this square system matrix is an upper triangular form. Everything below the main diagonal is a 0. We have numerical values above the main diagonal. and it has exactly the same solution as this original set of equations. However, the solution is straightforward to find, and let me illustrate that by writing out our solution, our equations longhand. We've got 1 times x0 plus 2 times x1 plus 1 times x2 is equal to 0. That's the first equation. We have 0 times x0 minus 2 times x1 plus 1 times x2 is equal to 3 is the second equation. And then the third equation is 0.5 times x2 is equal to 0.5. Now, this is the same set of equations as we started with, simply manipulated into a different form with exactly the same solution, but you can see that this will be pretty simple to solve when they are in this form. Okay, we can now work out the solution for this set of equations. The third equation, it's 0.5 times x2 is equal to 0.5, so x2 is equal to 0.5 divided by 0.5, which is equal to 1. We can use that result now and back substitute into the equation just above, and see if we solve this for x1, we will have 1 over minus 2, and then we have on the right hand side 3, and then move x2 to the other side, and we substitute a 1 in there, and then 3 minus 1 is 2, divided by minus 2, that gives x1 is equal to minus 1. We can use those results, substitute back into the equation for x0, which is going to be 0 minus, you move x2 to the other side, that's minus 1. Made a couple of mistakes. And then minus 2 times x1. x1 is equal to minus 1, so that turns out to be, make it plus 2 times 1. Minus 1 plus 2 is equal to 1. So that's the solution to this set of equations. I want to show this to you in symbolic form, because in symbolic form we will see a result that will show up in our computerized solution. For this set of equations, we at the end of our manipulations, we have a square matrix with A00, A01, A02, and then we have a 0, and then A11, A12, and then a 0, 0, A22. That multiplies x0, x1, x2, and that's equal to B0, B1, B2. So this is just a symbolic form for this set of equations that we have already worked out, which if we write this out longhand style, we get A00 x0 plus A01 x1 plus A02 x2 is equal to B0. A11 x1 plus A12 x2 is equal to B1, and then finally A22 times x2 is equal to B2. And we can write the equation, the solution, x2 is equal to B2 divided by A22. Then the next, working back toward the top now, the equation for x1 is going to be, we'll end up dividing by 1 over A11, and then we would have B1 minus A12 times x2. So we can then use the solution from the bottom equation, plug that back in, and find the solution for the one just above it. And now if I write the equation for x0, that's going to be equal to 1 over A0, 0. And now we have a B0 minus, and then we have minus A01 times x1 minus A02 times x2. Okay, so this is in general terms the solutions. Now if you'll notice, let me look at this last one and do a little manipulation. We still got 1 over A00. We've got this B0, and then I'm subtracting, and I'm subtracting a summation of these two terms together. I've got an A term multiplied by an X term, and I want to just leave it in that form symbolically, because we will see this form show up on our computerized solution. Here is a general set of n equations with n unknowns as described in your programming assignment. So we've got coefficients A00 times x0 plus A01 times x1 plus A02 times x2 plus as many coefficients as we need to A0 column n minus 1 times x n minus 1 equal to B0. Okay, so that's simply the first equation, and we have n such equations, and if we write them all out in symbolic terms, this is what the set of equations would look like. N can be any number of equations, not just 3, but 4 or 5 or 10 or 1,000, whatever it happens to be. This is the set of equations written in matrix form. There is a square matrix for the A coefficients, a column vector for the unknown values of x, and a column vector for the known values of b. The number in parentheses tell us how many times these numbers have been revised in the process of the Gaussian elimination. So it's there simply to keep track of the revisions that have been made. This is the algorithm in pseudocode for manipulating the values in the square matrix so that the values below the main diagonal will be equal to 0. We start at the top row k equals 0, and then using the row just below that, ki equal to 1, beginning with, it defines the multiplier m by dividing two values in the A matrix, and then using that multiplier, applying to each column across the matrix, calculating the new value for the entry into the square matrix. After it gets to the last column in the A matrix, it then does the corresponding entry in the B matrix, and then moves down to the next row, and thus goes through all of the rows below the top row, putting a 0 in the first column, and adjusting all of the other values in the A matrix as necessary. And then after all of the entries in the first column below the main diagonal are 0, it increments k. So now k is equal to 1, and it starts with row I equal to 2, this row 2, and repeats the process until all of the entries below the main diagonal are equal to 0. Here's the process shown graphically. We've got the A matrix shown on the diagram, as well as the B matrix. the algorithm starts at the top row k equals 0, and we work on the row just below that, row I equal to k plus 1. The multiplier is first determined by taking the ratio, in this case, of A10 divided by A00, and then applying the calculation first to column 0, and then to column 1, followed by column 2, all the way through the matrix to the final column in the matrix. And then don't forget, we need to go over to the B matrix and adjust the value in row 1 of that matrix as well. And then the process resets, increments the value of I, so we're still working with row k equals 0, and now looking at row I equals to 2, and it defines a new multiplier and then applies the calculation to row to column 0, where that will result in a 0 entered into the A matrix, and then adjusts the values in column 1 and then column 2, and then through the rest of the columns of the A matrix, and then the corresponding value in the B matrix. Then I is incremented repeatedly until it gets to the final row in the A matrix. A new multiplier is calculated, and that multiplier is applied to all of the entries in the last row of the matrix, resulting in a 0 in the column 0, and then adjusting the values in column 1 and column 2, and all the way through the rest of the matrix, and adjusting the value also in the B matrix. Now that we've gone through all of the rows with k equal to 0, k is incremented to 1, and we work on the row just below row k equals 1, so that's going to be row I equal to 2, and starting in column k equal to 1 again, defining a new multiplier, then applying that multiplier to all of the entries, first in column 2, and then, in column 1, then in column 2, then all the way through the J matrix, and then updating the value in the B matrix. And now I is incremented, that continues until we get to the final row of the matrix again. A new multiplier is calculated. That multiplier is applied to adjust the values in column 1, then column 2, then all the way through the rest of the columns in the square matrix, then updating the value in the B matrix. And this process is continued until we achieve a square matrix that is in the upper triangular form, so that we have values of 0 below the main diagonal and other values as they have been adjusted above the main diagonal. Now we are ready to complete the solution by working the second part of the program. We've put the system of equations into the upper triangular form. It is quite easy to find the solution for the last value of x in the matrix by simply dividing b by the appropriate b value by the appropriate a value, and then using that solution we can substitute back into the previous equation to find the value of x for n minus 2. To achieve that, you can set up a loop that starts at row k equals n minus 2 and steps backwards up to k equals 0, and calculates each of the solutions individually using using the solutions that we have previously found. Now, for each one of these solutions in this outer loop, you have to set up an inner loop to do this summation for the a factors times the corresponding x factors. Now these x's we have previously determined by our calculation. And when we accomplish this, we will have found all of the x solutions. The program is to be written so that the user can input any number of equations in the set of equations as the user desires. Now that is the end goal of the program, but I recommend that for the process of writing the program and debugging the program, you limit the number of equations to a fixed number. I recommend that you set up the program to work with 3 equations and 3 unknowns for the debugging process. So if you declare a constant integer n equals to 3, then you can use that integer n to declare the A matrix to hold the constant A values as a n by n matrix, the B matrix n elements long to hold the constant B values, and then the X matrix also n elements long to hold the solution to the set of equations. Remember, this set of 3 equations is just temporary to give you a set of numbers to work with while you debug the program. As you write the algorithm, you will want to print out the values in the A matrix. Here's a set of loops that can print out each of the values in the A matrix in the form of a matrix, and then you can also print out the values in the B matrix in the form of a matrix. Use this to test your program as you are writing it. After you have perfected your program using a set of 3 equations and 3 unknowns, you need then to go back and rewrite the program so that you can use any number of equations in your set of equations. And to do this, you're going to need to allocate memory for the 2-dimensional A array and the 1-dimensional B array dynamically. So you need to write the program so that you prompt the user for the number of equations in the set of equations, and then using that number and this recipe, you can then allocate memory locations for all of the elements in the square array, and you can also allocate memory for the numbers in the 1-dimensional B matrix. As we always do, you need to document the program with a written description of the program and the structure of the program, a flowchart to graphically display the structure of the program, a code listing for your program, and then screenshots that demonstrate the operation of the program using sets of 3, 4, and 5 equations that are listed in the description of the programming exercise. And I want you to write the program so that you prompt the user for the number of equations that the user wishes to enter, either any number that the user may wish, and then you have to prompt the user to input each one of the coefficients individually so you can populate the matrices, the arrays, and then after that run the program that will solve the set of equations. As you can see, that would be quite tedious to do all of that prompting and entering every time you wanted to run the program during the testing process. But once you get the process perfected, you can then write the program so that the user may enter any number of equations and the coefficients for any number of equations, and then run the remainder of the program to find the solution to those equations.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
the popcorn can't be beat. The sparkling drinks are just dandy, the chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves